What?
So it sounds nice for physics.
Yeah. So let's take a little while. We're not going to finish this higher derivative section today, and so just this stuff won't be on the quiz for Friday. But I just want to introduce the concept. The concept of a higher derivative is really like mechanically simple. Conceptually, like what we're doing to the function is simple. And we're going to see that as we work through this. It's some new notation that we're going to see. And then there are certain scenarios in which an application, we might have a way to interpret what a higher derivative means. So let's say we have a function, 5x cubed minus 2x. We love that function. It's a polynomial. That means it's easy. There's no products. There's no chain rule to worry about. Let's find y prime, or dy dx. Let's find its derivative. What do we get? 15x squared. Minus 2. Yeah.
Feels wrong.
What? Yeah, right. Well, good, doesn't it? So now we're at the point where this just feels easy. That's good, right? Okay. Polynomials are easy. If you take Calc 2, there's going to be a whole unit where we're just like, can I just make everything into a polynomial? And we work really hard to find a way to do that. Yeah, it ends up being like an infinite degree polynomial, but a polynomial nonetheless. So anyway, yeah, polynomials are easy. So now this guy right here, right, this y prime, this dy dx, it's a function of x in its own right? If I know what x is, I can figure out what the derivative is. If it's a function of x, I can find its derivative. Let's find its derivative. What do we get? 30x. Yeah, 30x. So the one we found first, 15x squared minus 2, that's the derivative, or what we might call the first derivative. And that name implies that there are maybe other derivatives. So if I take the derivative again, the derivative of the derivative is a second derivative. We use little 2 tick marks. Or d squared y dx squared. I'm going to explain this notation a little bit. Because the little superscript, I say squared, we're not actually squaring something, but the reason the superscript is on the d here is because we're taking the derivative twice. The reason that it's on the x here is because we've respected x both times. So derivative with respect to x of dy dx. That's also a function. We could take its derivative, get the third derivative, 3 tick marks, d cubed y dx cubed. What do we get? 30. And then we could keep going. Now, the higher the derivatives, with the prime notation, you could just be swimming in a sea of tick marks. So we kind of switch, and we use a little, put a little 4 in parentheses as a superscript. The parentheses are important because we don't want to make it look like y to the 4th. Without the parentheses, that already has a meaning, right? So that just means the 4th derivative, or we don't have to make any adjustments to this notation.
Do you normally switch over at 4? Like from tick?
It's probably, like 3 or 4, I would imagine most people do. I just get to a point where it's easy for me to distinguish 1, 2, and 3 tick marks. Beyond that, it just looks really busy. So, and more often than not, I just use this notation. So, what is the 4th derivative? 0, yeah. And in fact, if I keep taking the derivative, what do we always get? Yeah. So we'd say this is 0 for n greater than or equal to 4. We happen to get all the way down to 0, right? Once you get to 0, you don't go any further. The derivative doesn't change. That will happen if your original function is a polynomial, and only if it's a polynomial, meaning positive integer powers on x. It doesn't happen if you have negative or fraction powers on x. But just positive whole number, powers on x, you'll eventually get to 0. And a polynomial degree n has precisely n non-zero derivatives. So the last non-zero derivative was the third derivative, and we started with a polynomial of degree 3. So higher derivatives just means take the derivative again. There's no new rules to learn, okay? There's no new techniques, no new rules. Just need to know, like, how many times are we taking the derivative. Now, because with a polynomial, we know we'll eventually get to 0, that means when we see a question like this, find the higher derivatives. And they've given us this. It isn't multiplied out, but it's definitely a polynomial. Like, if I were to multiply it out, we would get only positive whole number powers on x. So when they say find the higher derivatives, they mean find all of them. Like, you're eventually going to get to 0. And there's a couple ways we could approach this, but I would posit that it's probably easiest to just multiply it out first. We'll do a little algebra, and then all we have are polynomials. Just power rule all the way down. So we've got a factor of x, and then if we square out x squared minus 1, we get x to the 4th minus 2x squared plus 1, and then we can distribute the x. This is just f. We haven't taken a derivative yet. But since we did this little bit of algebra, all the derivatives now, I mean, they're just going to be pretty quick. So let's find f prime. What do we get?
5x to the 4th.
Minus 6x squared.
Mm-hmm. By the way, if you look at the f of x after we multiplied it out, how many non-zero derivatives should we expect to get? 5, because it's degree 5. The 5th derivative should be a constant, right? And then we'll get to 0 after that. What's the second derivative?
20x to the 3rd minus 12x.
Mm-hmm. How about the third derivative?
60x to the 2nd minus 12.
Yeah. The fourth derivative? Say that again?
120x.
120x. How about the fifth derivative? 120. And then what about the sixth derivative? 0. So in fact, all the derivatives thereafter are 0. So I'll just say that the nth derivative of x is 0 for n greater than or equal to 6.
Is that how you want to do it now as a general rule? Once you get to 0.
Yeah, or, you know, if you wrote something like all the rest of the derivatives are 0, something that implies that you understand that is good. This is, I think, the conventional way to denote that. Questions on that example? Okay. All right, let's go ahead. Let's do one more. We have time. We want to find f double prime of -2 for this function. So we just want to find the second derivative as a function, and then we can evaluate it when x is -2. And if you're going to find the second derivative, the first thing you need to do is get the first derivative. If I'm going to find f prime of x, what might be a useful first step?
You have to use the quotient.
We can use the quotient rule, but we don't have to. And how do I know? There's no x on the top. That means that if I use the rules of exponents to rewrite this, like, what does it look like? How can I rewrite this function?
2 times 1 over minus x.
Sure, but what is 1 over? Like, if I use the rules of exponents. Yeah. So, yeah, it's the stuff to the -1 power. Like, this puts it in what I would call a power rule friendly form. If there were an x on top, the only thing that this move would accomplish is changing a quotient rule to a product rule, which isn't really necessarily less work. But because there's no x on top, that means I can totally avoid that scenario. It is made legitimately easier. Now, if you didn't see that and you went ahead and used the quotient rule, go for it. I mean, you'll spend like maybe 2 more minutes on it. It's not going to be like a huge deal. All right, who wants to have a go at finding f prime?
-2 times 1 minus x.
You go up.
To the -2nd power. Are we done? Say that again. Times y times -1.
You have to take chain.
Yeah, chain rule. So I can simplify this before we keep going, right? -2 times -1 is a +2. So now if we find the second derivative, who wants to have a go at this? How do we start?
-4.
-4.
Sorry, 2x. Or, no, sorry.
Oh, whoops. Why is that? That's not an x squared. That was me just putting something in there.
Then that's -3
Mm-hmm.
times -1.
Mm-hmm. Now, we want to evaluate this at -2, so I'm going to simplify it, and I think I'll just put it back in fraction form. I think it'll be more convenient. So if I would put this back in fraction form, we get a +4 over 1 minus x cubed. And that means that we can evaluate now when x is -2. So that's 3 cubed, 4 over 27. All right, so we had found the second derivative for this function 2 over 1 minus x, and I wanted to look at what about the function 2 over 1 minus x squared. You know, when we did this first one, we said, okay, because it's just a constant up here, right? If I rewrite it with a negative exponent, I don't have to use a quotient rule or product rule. It becomes like legit easier, right? We write it in this product rule friendly form. And then this first derivative we get, and then we just want to take the derivative again, and that same technique works, right? We just keep that negative exponent, use the power rule. So I'm gonna go onto a separate page for this. So if I wanted to find the second derivative, we start as we usually do with the first derivative, and that same approach works, right? Because the top is a constant. So if I rewrite this by writing the bottom to the -1 power, right, I could still just use the power rule. And what do we get? Who wants to have a go at finding the first derivative? How do we start it?
-2, parentheses 1 minus x squared to the -2 power times x, 2x.
Close. -2x. Right, because of that guy right there. And then, we could simplify this a little bit. So we have 4x times 1 1 minus x squared to the negative 2. So this is now qualitatively a different process to get the second derivative. I mean, we're still just going to find the derivative of the derivative. But the idea here, or what's really important to notice, is that after we take the derivative, we can't just use the power rule. What do we have to use?
Chain rule.
Well, yeah. What? Say that again?
Product rule.
Product rule. It's a product rule. When I use the chain rule in the first, right, in the one that we had like in our notes, that chain rule we just multiplied by a constant. So just using the regular general power formula, which includes the chain rule, sufficed. But here, the basic form, the basic structure of the function changes. And so when you find the first derivative, you've got to really stop, think about this as a function in its own right, like take a look at it with fresh eyes and say, okay, how do I do this? And so here we got to use the product rule. So our first function is 4x. So that derivative is 4. Our g function, what is g prime here? Nope. How do we begin? Like, we have parentheses to a power. It's the same thing we did to find the... I mean, how did we get the derivative of this?
Bring the negative 2 down.
Yeah, we're going to use the power rule. Then what?
The stuff.
The stuff. Mm-hmm.
Times.
Am I missing anything here?
Next column.
Yeah, what? Negative third. Yeah. So this is a positive 4x, 1 minus x squared to the negative 3. So then we get g f prime plus f g prime. You know, and then we'd have to simplify, right? And actually, this is a good review. How do I simplify something like this? Yep. Is there anything else we can take out? Yep. So we're going to take out a 4. And what's the lowest power? Mm-hmm. Then what goes in the parentheses? Okay. It's very generous of you.
X squared.
What?
X squared.
I mean, so that's the second term. Actually, the 4x squared is the second term because we took this out, so we need that.
1 minus x squared.
Ah. Yep. Because we took out the 4, right? And then these powers differ by 1. Right? The way this factoring works is always the same way. In one of these terms, we're going to need the parentheses just to the first power, so we usually don't write that power. And in the other one, we don't need it at all because we totally took it out. So this looks like 4 times the stuff in the brackets is 1 plus 3x squared over 1 minus x squared cubed. So, I mean, my broader point here is that once you find the first derivative, make sure you stop and just think about what it takes to differentiate that function. Sometimes there might be something extra involved after you take the derivative, after you find the first derivative. We didn't need the product rule for the first derivative. We did need it to find the second derivative. You want to do another one? Okay, you know how you make something more fun in calculus? By doing it again and by saying, let's do it with an implicit function. Here's an implicit function. This is an ellipse, right? Centered at the origin. I think it's oriented horizontally. And we want to find the second derivative. So, yeah. We'll start, we've done first derivatives with, implicit functions. That's what that whole last section was about. So I'm going to start. Here's our equation. Something super cool is going to happen in this example, so I just want everybody to be primed for it. This is going to be great. So the way that we begin just finding a derivative for an implicit function is we just differentiate both sides with respect to x here. So the first term, what do we get?
4x,
Yep. How about that second term?
6y d, y dx
Yeah, why do we need the dy dx?
with respect to x.
Yeah, and y is not x, right? If it were a z term, I'd have to multiply by dz dx. If it were a w term, I'd have to multiply by dw dx. So that's the chain rule. I have to multiply by the derivative of the stuff being squared. That's dy dx. So I'm going to, I think because it's convenient, just divide through by 2. So we have 2x plus 3y dy dx. And I'm going to go up here. I'm going to find the first derivative. I'm just going to kind of let it lie there for a moment. So 3y dy dx is equal to 2x, and if we divide by 3y, we get dy dx equals 2x over 3y equals, sorry, that's a negative 2x, right, when I threw that over there. So there's the first derivative. Now we have options. We could use the quotient rule on that first derivative. I find it convenient, though, to take our equation, which I have carelessly omitted the equals from. Of course, then it's not an equation anymore if there's no equals sign. So we've got this equation that involves the first derivative. Let's just differentiate this again. Let's differentiate this equation with respect to x. And if I do that, what do we get? Who wants to start us out? 2, yep. What do we need to do here? What is that? That's a product, right? I'm multiplying two functions. Y is a function of x. dy dx is also a function of x. So I can just use the product rule on this. I don't have to change how it looks, right? There's my f function. There's my g function. So f is equal to 3y. Then what is f prime?
3.
Close. 3 dy dx, yeah. Now, if g is equal to dy dx, what is g prime? Guess I'm asking, what is the derivative of dy dx?
You have to do the quotient negative 2x and 3y.
No, it's the second derivative.
It's the second derivative, yeah. The derivative of the derivative is the second derivative. So this is,
This is so cool.
there it is. And that's good for us. Let me just explain to you why this is good for us. We're going to use, right, we're going to use that stuff, we're going to, with the product rule, right, we're going to put together the derivative of this product here in our equation. And of course, the other side will just be 0. But what we end up with is an equation involving the second derivative of y. Well, it's a good thing that happens since that's what I'm looking for in the first place. It would be very suspicious if that didn't happen. So, yeah. So, just in the same light where there was one product, this was a 3y, but like if f was just y and I said what's f prime, you would say dy dx. Because the derivative of y is dy dx, right? So in that same spirit, if the derivative, if g is dy dx, its derivative is the second derivative of y with respect to x. So let's put this together. G times f prime. I'm going to multiply these two guys together. So that's 3 times dy dx squared. Do not confuse that with d squared y dx squared, because I have a dy dx times a dy dx when I do that g times f prime. Both of those have a dy dx factor. Plus f times g prime is 3y times the second derivative. So here's where we differentiated once with respect to x, and then here we differentiate again. Now the reason, when we differentiated once, I was like, let's go ahead and just find dy dx. And the reason that we found dy dx is I can plug that expression in right here. So here we're squaring dy dx. I know what that is in terms of x and y. And that's good for us. I have the original function in terms of x and y. If we find the first derivative, we can express it in terms of just x and y. If we find the second derivative, we want to be able to express it just in terms of x and y. It shouldn't depend on x and y and dy dx. Right? We should still just have it be able to express it in terms of just those two variables. So we're going to make a little substitution. So that's a negative 2x over 3y squared plus 3y squared y dx squared. The rest of this work is algebra. Now it's no small bit of algebra, we're going to have to work it out, but it's certainly well within our skill set. I'm going to pause here for a moment and see what questions y'all might have on what we've done so far.
Could we, so if we didn't want to do all of this, could we do the quotient rule on that first dy dx? Okay.
Okay, so let's do the algebra. I'll answer your question a little bit further, Xavier. You would still end up with kind of some of the same kinds of considerations, because you'd be using the quotient rule here. You'd still have a dy dx show up, right? Because that involves a g prime as well, and you still have to substitute that back in, and there'd still be a whole bunch of algebra. So yeah, it's definitely an option. I don't know that it's necessarily less work. It's probably not more work either. So I would start this by just squaring out the negative 2x over 3y. So that's 4x squared over 9y squared. We know that in general what we want to do is isolate the second derivative term, right? Like get everything over, except, get this alone, so move everything else over and then divide by 3y. But I want, it's not the first commandment, it's like maybe the fifth commandment of algebra, but fractions within fractions are definitely not simplified, okay? So if I were to do that now and do all that division, I'd have fractions with fractions, I still have a bunch of work. So what I like to do is front load that work and simplify as much as possible and then clear denominators. Then when I isolate and divide, I don't have fractions inside of fractions anymore. Kind of avoid that pitfall. So 3 goes into 9. We can reduce this product here. So we have 4x squared over 3y squared plus 3y times the second derivative. Now I want to clear my denominators, so I'm just going to multiply through by 3y squared. Multiply both sides by 3y squared, and obviously it'll distribute on the left. So distributing through that factor of 3y squared, we get 6y squared plus 4x squared, because in that middle term when I distribute it, it'll cancel the 3y squared. And then when I distribute to the next term, we get a 9y cubed And on the other side, it's still equal to 0. Now I'm going to throw everything on the other side, except for the second derivative term. So this is a negative 4x squared minus 6y squared. I'm going to do two things at once, but they're both fairly simple things, and so I hope that this is okay. I am going to divide both sides by 9y cubed. At the same time, I'm going to factor out negative 2 from that expression. So right now, we're feeling pretty good because, look, we have the second derivative and it's written only in terms of x and y, right? Which is our overall goal. But also, what I'd like you to do is just take a look at this right here, that expression in the parentheses, and ask yourself if you've seen that somewhere else in this problem.
That was our original.
So in the universe that is this problem, 2x squared plus 3y squared is always equal to what? 6. So in fact, this is equal to negative 12 over 9y cubed, or if we cancel a 3, we get minus 4 over 3y cubed. There's your second derivative. And as it turns out, the second derivative of y with respect to x depends only on the y coordinate.